Hi there. We are in chapter 12, section 5, and it is on graphing parabolas in standard position. The first part of this section kind of gives an overview of parabolas and the idea of having a parent function that is then changed in different ways. So the parabola is just that U shape that we get when we have an equation that has an x squared in it. So these are like quadratic type things that we've dealt with already, that we've spent a lot of time figuring out how to factor, how to get zeros for, all of those things. And that's what helps us with doing all of this stuff that we're doing in this section. Sorry, I had a text distract me. It takes me away from what I'm talking about. All right, so this first example here shows us, so that's a function that's an x squared function, but it's f of x equals x squared plus 1. And if you solve that and try to find the zeros, so if we set it equal to 0 to find the zeros, and we subtract 1 from both sides, and we take the square root of both sides, we see that we're taking the square root of -1. And we can't do that. So that means that this function has no real zeros. And I talked about this in my video the other day. When we're graphing a parabola, if it crosses the x-axis in two places, it makes it easier in some ways for us to find the zeros where it crosses. We can find the vertex, like we did in 12.4, and we can graph that really easily. However, they're not always going to cross the x-axis, so they could be up here, floating above, or out here, or down here, or over here, or over here, and none of those are going to cross the x-axis. So that means that there are going to be no real zeros. So solving it this way to find the zeros isn't going to help us in this situation. So they show you what this function looks like if we graph it. So you're going to be doing your graphing this way for today's lesson at least, where you have -2, -1, 0, 1, and 2 as your x values. Those are just really easy ones to use, especially because all of the functions that we're going to graph today will be centered. They'll actually all be at the origin for the vertex. So that's kind of the important thing there, is where that vertex is at. So for today, all of ours will have that vertex at here, actually at the origin at 0, 0. So notice this is x squared. It's our regular standard x squared function. The only difference is that the parabola is shifted up 1. And that makes sense. Look, they took x squared, whatever that was, and that was the f of x, and then they added 1. So all of my y values, remember your y and your f of x are the same thing, all of those values are shifted up 1 more than they would be. So this is easily graphed by finding those 5 points. Your 1 in the middle, and then 2 on either side of it. Okay, there are no x-intercepts because there are no zeros. So again, there's some general information for this, for the next few sections for this topic, not necessarily for today's specific assignment, but these are, it's good to see an overview. So we're going to talk about translational graphing, what transformations look like when we have a parent function. So our parent function is here, that we're looking at. We're specifically looking at the parent function, f of x equals x squared. As you move on in algebra, you'll deal with lots of parent functions, not just the x squared function, but lots and lots of parent functions. So the nice thing is that there's a lot of similarities in how they're changed, how they're transformed by the things that happen to the x squared. So one of those things is a vertical reflection. Okay, so that's where we flip vertically across the x-axis. So f of x squared, or f of x equals x squared, I'm sorry, becomes f of x equals negative x squared. They've simply taken that parent function and flipped it. Okay? F of x equals x squared is again here. And then when we add something to it, it shifts our graph up. Or if we subtract something from it, it will shift it down. Okay? A horizontal translation means that we are moving this way with our graph, that we're sliding it side to side. So here's the original, f of x equals x squared. And then if we add something to x before it's squared, that will shift it. This one's a little bit different, and we're not going to talk about it today. But if you notice here when it's plus c, it's actually shifted to the left. It's backwards from what we would think. The standard form for this is subtraction. So if you're subtracting a number, that's how many it moves to the right. And if you're adding, that's how many it moves to the left. It's a little counterintuitive, but you'll just learn that as you go along. But again, for this lesson, you don't need to worry about that. The thing that we're going to talk about today is vertical stretch or vertical compression. So if we have our original function again, f of x equals x squared, vertical stretch or compression, either one, are when you multiply your x squared by a factor. So if we look here, it says the function is either stretched or compressed vertically by the multiplication of a constant after the function's been performed. So it's after you square the x that it gets multiplied. That's what's important here. After it's squared. So in this you would square the x first, and then you would do that. Okay? So the vertical stretch occurs if the absolute value of c, so whatever c is, if it's greater than 1, then you're going to have a stretch where it stretches and it makes the graph skinny. Like think about like if you stretched out like putty, it would get skinnier. Okay? And a vertical compression occurs if the absolute value of c is less than 1. That means if it's like a fourth or 3/4 or 7/8 or 0.925, something that is between 0 and 1, then you're going to have this called compression where it squishes it down this way, and so we get this kind of bowl shape effect rather than this skinny stretch. So this is a stretch and this is a compression. And if you think about what we've learned about slopes, when we have a slope that's like a big whole number like 5, it's a really steep slope. And when it's like 1/5, it's a really shallow slope. So that kind of makes sense when we're talking about stretching and compressing, that this is going to make me look tall and thin, stretch it out, and this is going to squish it like that. Okay. So today we're focusing on vertical reflections and stretches and compressions. Okay, so if it's a negative or a positive, so that will tell us whether if the cup is up or if the cup is down. Okay, and then stretching or compressing, if we're making it stretched up and skinny, or if we're squishing it out and making it more like a big wide bowl. So our parabolas are going to have zeros at the origin because we're not doing a vertical translation up or down, and we're not doing a horizontal translation left or right. So notice with the reflection and the stretching and compressing that my vertex stays at the origin, 0, 0. So when you graph, you are going to take your function that they give you. So this is an example that you have. you're going to take the function you're given, and the first thing they want you to do is compare it with a parent function. So if I look at this, I know that this negative tells me that I am going to have a vertical reflection because it's negative. So it's going to be flipped this way. And the 3, so that's what this tells me. And then the 3 tells me that I'm going to have a vertical stretch because that's a number greater than 1. So I'm going to have a vertical stretch. So it's going to be upside down and it's going to be skinny. So the easiest way to do this, I'm going to use this table, and you'll use the same table when you do yours. So I have -2 to 2 for my x values, and then I need to just find f of x for each of those. So I'm doing -3 times -2 squared, -3 times -1 squared, -3 times 0 squared, -3 times 1 squared, -3 times 2 squared. Notice all of these that I'm squaring the x before I multiply by that negative number. That's really important. Okay, it's not -3x squared, it's -3 times x squared. So this would be 4 times -3 is -12. 1 times -3 is -3. This is 0. 1 times -3 is -3. And -3 times 4 is -12. And that makes sense because it's a parabola. We're going to have repeats like that because we're looping around. So I'm going to graph -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. -1, -3, 0, 0, 1, 3, and 2, -12. So now I can graph my graph, and I'm done. So that's your job for this section, is you look at the function they give you, you compare it with the parent function, and you're only going to have 2 things happening at most. Some of them you won't even have you won't have both. So if it's a negative, you have a reflection, and then if it's a number greater than 1, then you're going to have a stretch, and if it's a number between 0 and 1, then you're going to have a compression, and it's going to be more bowl-shaped. Okay, so like if it was more bowl-shaped, it would be more like this, where it gets stretched out like that. So this is stretched, like we're stretching it like we would like a piece of gum or something, how it would get skinny if we stretched it. And this is compression, where if we squished it, it's going to get wider and fatter. Okay? So for 12.5, you can do the blues. There aren't a lot of them. Hopefully that will give you what you need. This doesn't have the answers, so I will, I'll have to draw those up for you and have that for you after you finish these. Okay? I will see you next time for 12.6. Bye.